I think, oh, really?
Oh, I think Luke is trying it out. So, he asked for.
Anton is recording, and I put the link probably, yes, from Anton in the web page tomorrow on today's.
Yeah.
In any case.
I can also share the recording with everyone. I mean, we always share it at the end.
Sure.
It doesn't matter. How do you just put it into a Dropbox when you share?
Well, I usually upload it to YouTube.
Yeah, I know. But
if you have Dropbox, I could send it to you. Yeah, I think. Yeah, I could send it to you.
To just record it and do my own
thing. Yeah, that's fine.
You know, be independent. You know.
Makes sense.
Yeah.
Okay, it's so you can start whenever you want, but usually it's good to wait like till 5 past.
Pardon? Do we wait a couple of more minutes, or do you want me to start?
As you want. So we usually start at 5 past, but just do.
Yeah, okay. Let's just wait a couple of minutes. You know, it's the same on when I have it. People always come in right at the end. You know, near the time. So
you can start with some introduction, maybe.
Ron?
Yeah. You can start with some introduction.
Yeah, okay, let's so let me share my screen, and it's this one I want. So, just move that over there.
All right, can y'all hear me?
Yes, I could hear you.
Okay, great. Okay, I got my mic fixed. Thanks, y'all.
Okay. Okay. Can you all see my pointer? That little red dot on the slide. Okay.
Yes.
Anyway, let me start. You all see my name, Anton Vrba. I'm actually an Austrian citizen. Grew up in South Africa, studied in South Africa, received a BSc Electrical Engineering. Initially, that was in 71 that I graduated. I worked in the fledgling semiconductor industry in South Africa, and at the university, we produced the first field effect transistor. And doing that, we had extensive physics in the electrical engineering course so that we could understand semiconductors. And that's, I think I had the equivalent of 6 semesters of physics in my engineering degree. So that is my background to this. I basically, after South Africa, I came to the UK, then to Austria, and my last professional work was in the UAE, building substations and working with 440 kilowatts. I always had a keen interest in physics, and the question that I wanted to answer is, what is a mathematical background, or what underpins Newton's first law, which we all know: a body in rest or in motion keeps its motion or rest unless disturbed by a force. We then had the parallel question: what is momentum? I usually start my talks to set the theme by going a bit on a what's it? Lost the word. on a philosophical point. And here I want basically in Einstein's 1921 paper, Geometry and Experience, I think that is the only paper where he actually quotes Poincaré, in that where they describe that you can choose a any geometry with a purport of physical laws, and if you combine this G plus P is subject to control and experience, and if that is correct, you can choose the remainder of P so that G and the whole of P are together on accord with experience. Typical model, which is basically a model building. It doesn't explain the what is below it. Then I found that Niels Bohr was very much an instrumentalist as well. He said physics is not to disclose the real essence of phenomena, but only to track down so far as possible the relations between the manifold aspects and experience. Then he states very clearly that the quantum mechanics abandons all pictorial representations, and he said that actually twice, and that the entire formalism is considered as a tool for deriving a predictive and definite and statistical character. So again, model building. And then going back to the Geometry and Experience paper of Einstein, this is actually right in the beginning that I first quoted out of the middle. Einstein writes, an enigma presents itself, which in all ages has agitated inquiring minds. How can it be that mathematics, being after all a product of human thought, which is independent of experience, is so admirably appropriate to objects of reality? He then asks, is human reason then without experience, merely betaking thought, able to fathom the properties of real things? He carries on. In my opinion, that is Einstein's opinion, the answer to this question is briefly this: as far as the laws of mathematics refer to reality, they are not certain, and as far as they are certain, they do not refer to reality. A nice way for saying, well, you know, that we use mathematics, but if we have if the mathematics is certain, we cannot it cannot be reality. Somehow goes against my grain and not my way of thinking about it. In reading Poincaré's paper on the dynamics of the electron, which was published in 1906, is this lovely statement in there. This state of affairs may be explained in one or two ways. Either everything in the universe would be of electromagnetic origin, or this aspect, shared as it were by all physical phenomena, would be mere epiphenomenon, something due to our methods of measurements. Now, I really think you should really think very hard about this statement of Poincaré, you know. So we've got all these models, they all work, but are they really describing the natural phenomenon or not? Inspired by, before going to that, new type of thinking is essential. In 1946, Einstein put out an appeal for essential thinking, but this was more in the form of getting rid of atomic weapons instead of new science. So I'm a bit misusing that statement there. But 2 weeks ago, Tim Palmer said on the Bell conference series, it just shows people are not thinking out of the box for the type of physical theory we may need to explain Bell's theorem. Now I'm going to ask you to think out of the box like I'm thinking out of the box, and take on the what I call a Poincaréan ontology. everything in the universe is described by Maxwellian dynamics and is not influenced by the method of observation. Here, Maxwellian dynamics is a study of interactions as nilpotent electromagnetic superpositions. When I say electromagnetic here, I say it is basically electromagnetic-like. You know, for certain, electromagnetism cannot describe particles as such, although we want to describe them as such. So I actually formed the term bimodal waves. So, you know, we'll come to that later. Let's go to the next one. Now let's begin. We all know the wave equation, so there's no need to talk about that. And now we choose our reference system, X, Y, Z. We know that a right-handed coordinate system is defined by these 6 vector equations. But now I want you to consider the cross product series. Z1 equals X0 cross Y0. X1 basically just going along these lines. And finally, this is an indefinite series. So we get Zn equals xn minus 1 or sub minus 1 and cross y sub n minus 1. So what do we need to do that this theory doesn't is continually expanding, that so that we basically have x0 equals xn, and then if we have that, we have a simultaneous cross product equation set, which applied to the electromagnetic phenomena looks like this. We all know the classic picture of a electromagnetic wave, as in any textbook. We have these 3 cross product equations. The one over the norm b squared and the one over the norm u squared are basically required. That this whole equation set can be solved simultaneously, and that what I said previously on the last slide, that we have x0, or basically the velocity 0 is the same as the velocity later on in time. And then we just need to integrate the velocity vector with dt to give us a position vector. So now this is a reformulation of the Maxwell equations. If I do a left-hand, right-hand curl operation on this equation and this equation, we basically get to we need to solve these triple vector products below, which each one has 4 terms. And this is very easy. You know, with a divergence of u, the divergence of b, and the divergence of e are all 0. The b dot u b dot del rather. Is it del? No, it's grad, I think. Times u is 0, because if we expand it out, we see that the velocity is of time only, so that the ddx's don't play any role. And then it leaves us with the convective operators, u dot nabla times b and u dot nabla times e. What are they? The textbooks give us this equations, which doesn't help us any further. This is a Jacobian matrix, but it is very easy if you write it out. It is just ddt. Therefore, this triple cross product evaluates to minus b dt, and this triple product to minus dE dt. In other words, we have the by doing the the left and right curl operations on these two equations, which was part of our initial set. We've now recovered the Maxwell equations as shown here, and we already established that the divergence of B and the divergence of E is 0. So basically, the next thing we have to prove is that actually C squared is 1 over epsilon 0 mu 0. And now I think, okay, before we go there, I now have a hierarchy of the Maxwell equations in the middle. My 3 sets of vector equations on the top, and at the bottom, on the third level, we have the wave equations. By definition of that I had in the first slide is any description that results in the wave equation is a wave. Therefore, this number 1 is a formulation of a bimodal wave. The bimodal because we have 2 modes, B and E, or electromagnetic wave in this case. And now also any solution to the wave equation is not necessarily a solution of 1. So basically, you guys who are doing physics, who are making up, you know, or solving or getting solutions for these equations, they might not be electromagnetic. So at this stage, I think before I carry on, is there anything that needs to be clarified of what I've said now? So anybody have a question or not? Okay.
Will you have time for questions at the end? Because there are some things I want to ask about, but I'd rather just let you go and wait to the end.
Yeah, okay, fine. By the way, regarding questions, each slide has a number on it. So if you just copy that number when you have a problem with a slide, and then at the end we can come back to it. As we can see, we've got 78 slides. Our sort of average minute to a minute and a half on a slide. So it's you know, it's basically so that I can navigate back. Okay, let's go to the next slide. Now let's take the nomenclature that I adopt. I say a wave P this is a bimodal wave and is a solution of, let's call this curly M UBE of these 3 cross product equations. So what I've adopted is that E equals U cross B is an activation by B. This you could also call it induction by B. Then the velocity vector 1 over B squared B cross E, I say is vectoring. In other words, I don't necessarily want to go in straight lines. And then we have the reactivation of the magnetic field by the by equation C here. So the I can want to describe a wave W parameterized by the solutions of this equation, and position is simply the integral of U dt. Okay, I don't think we need to go through this here. Basically, it's let's just start. Each vector has a unit vector and a scalar that scales it and carries the dimensions like meters per second for C. And then the B has got a unit vector and basically and a B to carry the units of B. Now I'll make two assertions. So basically the aim here is to prove C squared equals 1 over epsilon 0 mu 0 without resorting to any measurements or resorting to the work of Faraday and Gauss, I think, who determined epsilon 0 mu 0, I think. So basically, my two assertions that I make is that an elementary electromagnetic wave W exhibits power h over t squared, where h is a Planck constant and t is 1 second. Therefore, B would be an elementary field that we are using. And then I'll make the second assertion: an elementary wave transports an electric charge E every 1 second, which is a wave current. Now, this is nothing new here because partial E over a partial dVt, Maxwell had identified as the displacement current. So in a varying electric field. So I've done nothing. I don't think there is anything wrong with these two definitions. So if we got our three equations here, we now use the equation B, the one with U, and say this is an equation that carries the that causes the action, which is basically the pointing vector. The pointing vector actually is defined E cross H, but it has to be B cross E here. But we can talk about that later. Actually, we're not going to talk about it later, but it's in my paper that this is the correct expression of that the pointing vector should be. We now can basically we multiply this equation by H. What I've done here, I've taken out the vectors. I'm just working with the norms of it. And well, I'm missing something here. I'm doing it. Oh, I'm not missing anything here. I divide by C, which is that C there, and I multiply and divide by L to the power of 4, where L is an elementary distance equals CT. So, and the square brackets means that I'm developing a constant. So now we define the elementary electromagnetic action, which is basically the electric action is rho h, and rho is just basically 1 coulomb per kilogram, just to make the units work. And then we have action is momentum times distance. So it is basically the momentum is EC and a distance L, which is here with LEC. And I introduce a constant kappa because I need to scale it so that it gets to a value H. What the constant kappa is, I've got no idea, but we just have to put it in there. So otherwise, we can't make the assertion that HE equals LEC. We have to put in the kappa, this proportionality constant. Similarly, I say electromagnetic action is proportional to the product of B and the elementary volume which the wave occupies. Basically introducing a constant chi, the volume L3, and the norm of B. And bringing this all together, this equation here and that equation there gives me that B equals kappa EC over L squared and divided by chi as well. This value here. Now, we remember we had this equation earlier, and we now introduce the value for the norm of B, which we found on the last slide, which we introduce into here, and E equals CB, which we introduce here. And now I define and I mark that what I'm taking out of the equation, B equals H over kappa L squared E. Those are these terms that are in the maroon color here, but only if what remains here in black is equal to 1. So, which we have here. We now replace this B squared with the value of kappa that of B that we got earlier, and which reduces to the second line here. And for that to equal 1 requires 1 over chi as expressed on the right of that line. We put this in here, and then I say all that remains is to set kappa squared over 1 over 2 alpha, and we have epsilon 0 mu 0. So, or basically, we can express it either mu 0 in terms of kappa, or if you want to express it in terms of the fine structure constant alpha, we have to do the substitution in here. And these are the proper expressions for epsilon 0 and mu 0. So therefore, I now shown that 1 over c squared is indeed epsilon 0 mu 0. Therefore, the equations set curly MUBE are the Maxwell equations. So in my opinion, this is a very fundamental work, and the first time that epsilon 0 mu 0 are derived by in terms of mathematics. This repeat the coupling. Yeah. So okay, it's basically here. It will. What is the fine structure constant? I've now got another possible explanation for the fine structure constant, and namely that it relates to this coupling in basic electromagnetic theory. Now, this is a big what-if discussion here. Oliver Heaviside in 1892 presented us with the vector algebra that we all use in physics today. Planck proposed the quantity H in 1900, and Millikan published in 1913 the electric charge as 1.592 times 10 to the minus 19 C. So now I simply ask, what if Heaviside formulated this that equation set MUBE that I have formulated? Well, then we would have a Heaviside constant of kappa as equals to 8.277. I must make sure, yeah, it's correct. I thought the magnetic permeability would have transitioned from the fixed 4 pi times 10 to the minus 7 at that time into the expression h over kappa squared E squared C. And then in 1916, when Sommerfeld would have established the fine structure constant, we would have the relationship alpha to minus 1 is 2 kappa squared. So, you know, it's just a big if, you know, if we really want to think about the history of physics. But nonetheless, using the this expression rho h equals kappa LEC, rho is 1. We can therefore define the Heaviside constant using the codata and work out a elementary length of 1.66 times 10 to the minus 24 meters and a elementary time of 5.559 times 10 to the minus 33 seconds. If there's anything to be found in here, I don't know, but it is certainly something that we can derive from the work that I've presented. The magnetic flux quantum is phi 0 equals h over 2e. That has been observed experimentally. That is how it is defined in physics, and it's also derived by analyzing the Aharonov-Bohm effect. But now I have a different value. The phi, isn't that the psi? Excuse me. Over h over kappa e, which is not anywhere near to the quantized magnetic flux. But you know, so if this is a quantum or not, I really don't know. But expressed this way, I can now express the Pointing vector as S equals mu 0, 1 over mu 0, the norms of B cross E, which works out, well, if that's a vector, I shouldn't have the norms in here. Sorry, c squared over m, which is exact units of the Pointing vector, you know, and confirms the assertions of earlier on slide 19. Now I have a question: who was first, you know, the chicken or the egg? And this relates now to the relation to the way that we define the speed of light is 1 over epsilon 0 mu. Not have been able to derive this. So in my opinion, there must be something else that defines the speed of light. Let's just call it transportivity equals c squared. Probably of some 2 elementary quantities yet undiscovered. Why I say 2 is, for instance, in fluids, the speed of sound is given by the coefficient of stiffness divided by the fluid density, or by the partial derivative of something I'm putting out there. I've got no idea what it is, you know, what these quantities are in vacuum that should give this expression. And this is where I actually planned another small break. And you see, we've gone through 30 slides and we've gone exactly 30 minutes, so I'm perfectly on time. Any questions at this stage before I carry on, or do we want to carry on like was asked, suggested earlier? Okay, let's carry on. Okay, now basically, let's just look at the traveling plane wave as we know it. It is given, this is a standard equation that we find in every textbook like Jackson on electromagnetic theory. The wave vector kn dot z, we can basically, the norm of it works out as double omega z over c, which basically reduces that equation to a x cos theta 0 plus y sin theta 0, and at the position z equals ct plus z 0. So this equation here, that I don't think you see when I'm moving the cursor, so let me just keep it still. So the equation on the bottom is equivalent to the equation that we have in every textbook. It is just differently explained. And we are actually only working in one plane of the electromagnetic wave. So basically, this is just repeating what we said. We are just looking at one particular plane, that is one arrow set in this picture. So let's carry on. Now, if I take solutions of these equations, they're actually very simple to find. They are simple rotation matrices. You call them Euclidean rotation matrices. So for a one-dimensional wave, a one-dimensional wave is like the radio wave. I've got one cos omega t. These are the, I'm only working in the unit vectors here. So this would be the for a plane wave. I can make the wave go in a circle because this is also a solution. Here, the velocity vector describes a circle. The magnetic field B is in the circle, and the electric field points upwards or downwards. And we can have a three-dimensional wave where we have the basically sine, what you call them, the polar coordinates, sine omega t, sine n omega t, sine omega t cos n omega t in the first line. Here, the magnetic field is so what happened, and if we, I think I hopefully have this on the next slide. No, I haven't. But basically, on what have we got? I basically formulated these all to be always have the magnetic field be exactly the same in all three equations. As these are all what you call it, they're all perpendicular to each other, these three equations. U forms the velocity vector is is circular, or basically three-dimensional, on a circular path. This is circular, always the same, and this one being you call them covectors, I think, will always have radiate outwards, but I'll demonstrate this later. So this is now basically what I've done here is, if I have the position as a integral of u dt, I basically describe a a circularized polarized wave this way, which is very much the same as we had earlier in Jackson. This omega zi over c, it is just an angle theta. There is no time in here, so basically it's the same equation that we had earlier. This is what I wanted to show you. This is a three-dimensional form. Actually, this is for a spin half particle. We'll come back to that later. And we can see that the velocity vector is always tangential on these lines. The magnetic vector is at right angles to it, and the electric field is radiating outwards. These are two further plots. Why they look different? Basically, let me just go back. So that you understand these plots. I have got this N with a dash on top, or it's a graph symbol. This is there's a mistake in, sorry, there's a mistake in this equation. But the this omega term here, and I basically change this value in graph. But I think there might be a mistake in here if I look at this now. But this is actually is a 1:17 ratio. So if we count these up, there are actually 34 of these. And because it's a spin half, they separated here. Whereas here, we've got a 1:1, a 1:2 ratio, which gives me this curve, a 1:3 ratio, which gives me this curve, and a 1:5 ratio that gives me this curve. These are all spin 1 application, and we see that these lines basically join up at the on the equatorial plane. The Z plane basically or the Z axis going through that hole and that hole there. And if we go back to this picture, we see that I've separated them from the same formulas very easily. We'll come to that later again. How have I calculated those curves? Is basically if I take in terms of omega 1 and omega 2, I have the velocity vector shown here. And doing the integral, it works out or evaluates into this. Excuse me. And the path is closed. It in periods of t equals 2 pi here. Basically, going back to this curve here, I think I've done these on scale. Each path is equal to path length is equal to 2 pi. So it's on these, which basically which we get out of because we've done it this way, and because we close in a period of 2 pi, and if you see one, it means the path has a path of 2 pi. Now, the SI jungle, as I call it. Our unit is joules per amps, and the magnetic potential, which is not normally shown, is basically it hasn't got a unit name here. It is not it's not in the literature. A magnetic potential of newtons per amps, and the magnetic potential field, or the Tesla, as newtons over amp meter. Working that way, I found this very confusing till I defined my own units. This JS brought together is basically a Planck, a joule second. So if I take the unit of a magnetic quantum or magnetic of a magnetic flux, and I've given it the name A here, that because I will carry on working in terms of A later on, is basically a Planck over a Coulomb. The magnetic potential, a Planck over Coulomb meter, and a magnetic potential field as a Planck over Coulomb meter squared. And the same for the electric flux. All that happens, we must bring in the constant C, which is adds a meters per second into that. This is basically the sort of unit system that I adopted to make sense of this all. I've introduced here symbols A and L and R. There is no, I haven't seen a definition for electric flux quantum. Neither have I seen the definition of a magnetic potential, which I put in L. I actually, in the future, I've decided to actually call these A dot and an A double dot, and there's also a three dots underneath, basically always dividing by an L, but that is in future work. But I will now carry on in terms of A and R, so that you know what A and R stands for. While on this, we've done the electromagnetic waves in terms of B and E. And the proposition is that there are electric potential waves and there are electromagnetic flux waves. We're now going to carry on with the electromagnetic flux waves. So this is basically the same definition here again. A solution for a quantized rotary wave would be omega 0. An integer quantity that we multiply this with. I need to bring in a L0 here and an A. We will see that on the next slide. Here we see what how, you know, instead of the standard picture that we had earlier, you must here think propellers. This is not a wave traveling forward. This wave only exists where it is shown. So this is basically three waves, or the same waves at three different time periods. And as it propagates forward, the whole thing rotates. So, you know, that's why I say think propeller or boomerang or whatever. And basically, I have to let it work over distance L0. Now, similar to slide 19, I have now two new assertions. So we are saying elementary rotary wave R has action H, which basically we know a photon has action H, because we multiplied by its frequency. And that the elementary rotary wave transports an elementary load. And the load is, I give it the units L, so I basically have got now L twice, and we call it the Leyden, honoring the Leyden jar. And yes, I'm hinting there's we need to separate the electrostatic charge E, that to the electric charge that drives our industry. I can prove it to you or give you a thought experiment to show that they are different. So basically that hinting is a bit more certain than what I've shown here in the slide. That's why I introduce the L written in mathematical script, so it looks like a big E. So if you don't like the L, just think of E, but E's won't work because basically I also need to make L complex later on. Certainly the elementary charge E is not a complex value, but this elementary load would be a complex value. So I now can go through the same actions here, which, as I shown earlier, to get to this formula, just repeating what we've done earlier. And instead of an epsilon 0, mu 0, I define an epsilon dot and a mu dot here. Same ideas again. I have a rotational action, which I call H sub rot. And basically, we know that rotary action is rotary momentum times the angle theta subtended, which comes to this equation here. Now, this is also something that I've been missing in the physics books, and I've been asking other people, has anybody ever talked about rotary action? Nobody has, so this is something that I see no reason why I cannot use it, because it follows the rotary to linear motions is very clearly defined in standard classical mechanics. So it is basically what I'm doing here. Instead of the kappa, I use this curly K. Do the same thing again, let's just go here. This we had earlier. The rotational action is also equal to 1 over chi L0 A0 from the wave. Same argument as I had earlier. We do the same sort of mathematical derivation, which you can all look at more in detail on the slides later on, or in the papers, and which basically reduce, then have an epsilon dot and the mu dot as these values here. We can discuss this 4 pi squared. Basically, I think if I need, basically that arises from this 2 pi in here. If it's needed or not, I don't know. It's if it's in there or not, it basically cancels out. And we have got no ways of measuring these or determining these values anyway. Or as far as I know, maybe it can be done. Now, what's happened here? Oh dear. I don't know why okay. Something went wrong on the slide. Basically, I'm introducing a new form or a new mathematical symbolism into matrix algebra, where these terms between these curly delimiters basically means it is a common factor for each line. So basically, the P check mark C only works on in here. So basically, I'm taking all the units out. So if I have a vector here, these are the unit vectors, the axes here, and the quantities and scaling in here. Now, unfortunately, this N with the box around it, which shouldn't have happened, I don't know why it's happened, should be actually an N with a check mark on top of it, like the P check mark, the Q check mark, and the R check mark. Basically, those are all the way that I can add quantum features to this equation set, to this solution. So if we look at this, a three-dimensional particle, as we've seen earlier, the X, Y, Z have gone off the screen there. I've got, let's look at the A check mark. The A check mark is, okay, let's go here into the M. M is N that I multiplied with. R check mark is plus or minus if it's right, if the rotational vector goes right way around, or the or clockwise or anti-clockwise. And W check is the how many times, or basically I divide basically N over W. M is NR, which is left right. N is scaling to scale the frequency, and the W is the closure. If W equals 2, I have to go around twice. In other words, a spin half particle for the path to close. So this defines the M. The N is any positive natural number, which gives us H equal NF0. The R check, we had the plus minus rotation. And I've got, this is in the XY plane, and I've also got a rotation in the, which I designate here as U, which is also +1, and this is a rotation in the from the XY plane to the Z plane. If you can think of the which basically goes into A here, which is, so this is X, this is on the X plane. There's the X component, Y component, and the Z component. So the Z component's got the X is any prime number or co-prime to N. We must multiply that frequency. We saw earlier these figures. I'll go through that again just now. The rotational direction. We can now basically we can determine the spin of the particle as the rotational direction. P, which we have up here, is the direction if it goes into the if the particle propagates in the positive direction or the negative direction over W. That is a spin. P is a property, charge polarity, the Q's here. And R is a linear scaling, which I introduced here. That linear scaling should actually happen on the potential waves, but I've got them in here. It's something that I've just discovered in the last few days. So a photon is parameterized by, unfortunately, simply with the direction that it's going. I need to bring a charge into it, an RL0. You know, you're taking it all over. The N with the straight box around it here, unfortunate. times the direction. And we can say that the quantized rotational action we defined as h rod k, the load, the elementary length squared, omega 0, and phi 0 was the angle subtended in one revolution. And this, if n is positive, we have nr2 pi in 1 second. Therefore, the rotational action is n r. That's r is plus minus 1 of this rotation. If we bring this into the Poynting vector, which is basically r is basically u cross a. If we remember from earlier, here we have it, r equals u cross a, which I substitute in here. And if we now evaluate this, we evaluate it to n r. These RQ are all 1, R squared L 0 H. We know that R is 1, Q is plus minus 1. We take L equals to 1 and we set R equals to 1. We get the action as NH. Therefore, E equals HF. I hope you understood this, or I can go over it again, but it's also explained in the in my papers. So this is the first time that from straight mathematical point of view, from having these rotary waves, we did, have an idea, or basically leads to the Planck formulation of the energy frequency equivalence. Okay, so here we have the same again. Basically, what I showed, what M½ does is basically, I explained this earlier, with a spin 1 in this, what I call a spin 1, maybe it's not spin 1. These two paths join on the equatorial plane, and on the, if we introduce m equals a half, these lines are opened up, and because now the path length is 2 pi, the whole thing gets has double the diameter of this one here, because the number of if we count along up top here, these lines are the same amount of lines we count on any point along the equator here. Any questions? I think I must have confused a lot of you by now.
What happens at the poles where the magnetic fields seem to be pointing in opposite directions?
At the poles, no, the magnetic field is, I can never go across a pole. That is impossible. You know, that it will always have this hole in the top. The magnetic fields will are horizontal. Let's let me just think. Yeah, I must basically plot this out. You know, that U is along that direction, E is out. The magnetic field will be pointing out here. Basically, it will be the magnetic field will be at right angles to this, and basically Okay, I've got it. The magnetic field at the equator will go around the equator and come back here. The magnetic field up top here will actually go, be pointing this way. And if it needs to close up, we'll navigate this sphere and close up here again. Because the magnetic field is both the velocity and the magnetic field are tangential to the surface of these figures, and the electric field is always pointing out.
Yeah, so I thought the magnetic field near the pole would point toward the pole.
It would point or it could point outwards. If it points towards the pole, it would be the same thing. But a magnetic field needs to close up, and basically each line can be. You can add another. You can superimpose now 34 of these waves on top of each other without them ever clashing. Whereas here you cannot do that. You'll have a clash on the equatorial plane. So basically, you can superimpose 34 of these rotary waves on top of each other here. So, and then, you've got 34 lines up top. So and then basically, if the one moves into the opposite direction to the other, we'll have 17 rotary waves on the top and 17 rotary waves at the bottom, and the magnetic fields will basically you'll somehow close up on the surface of the sphere to the other ends. Okay. Let's carry on further with this. We said as if we have this path vector and we co-primes this. Now the distance, basically I'm calculating the radius of that sphere that you've seen, which basically, or the vector P, which evaluates to this, and is, I think I made a mistake here. There should be a smaller than, was it greater? But okay, the R phi is must be greater equal to C over W. But so where I'm going to here is if I cannot put I'm trying to work before we've worked out E equals HF, and here the action is now no longer dependent on the frequency of the rotor, but rather on the dimension of the sphere. And if we can, now here comes a big thing. If I want to calculate the energy of a particle that it holds. So previous slide we came to the action, and but A should not extend over the geometric center of the path, which limits us to that RL0 must be smaller than that Rphi, and using C equals L over T, and omega 0 is 2 pi over T0, which we then we use the right-hand part of phi, and we substitute into it the omega 0, the C L0 over T0, and it reduces to the Rm1 over 2 pi x check, which we then put into the action into there, which if we multiply action, or rather divided by time, we get the energy of such a particle as h bar r over x check t0. That, in other words, the x check is the co-prime to the that which moved into the z direction. In other words, the more let's get back to this figure here. The more of these I put in, the energy reduces. You know, so if this is 17 times, the energy has is reduced. Therefore, basically, if I then load it up, that each of those lines that we saw in the figure has got a rotor on it, that x check mark, that point will disappear. But the takeaway here is that that the energy is proportional to h bar r. In other words, the bigger the part that sphere is, the more energy it carries, and the bigger it is, actually the lower the frequency gets of the. I'm sorry about these ends that have not, for some reason, gone wrong here. So this is what I said just now. Energy scales proportionally to R, or inversely to mx squared. M, if we remember, has got n in, that's the divided by the closure. Okay, now I said I want to make the load complex. So I go now analyze all of this in a complex space, so that the x-axis becomes a xi plane, the y-axis becomes a yj plane, and the z-axis becomes a zk plane, where I, j, k are basically complex. So in other words, I have a 6-dimensional space with 3 dimensions being real and 3 dimensions being complex. One could look at it also as a quaternion type of space, because if I have one axis is real, with it I have 3 complex variables. I haven't gone that way yet, but basically what I'm showing here, if I make the load complex, I can requires either that the velocities get complex, or the conditions. There are 3 conditions which hold, so that all these to solve the equation set. But basically, we're now introducing a complex velocity in the space. It's something that we really have to get our head across or mind across, that we can have complex velocities. But this allows me to superimpose a photon and the three-dimensional construct of earlier. I introduce the complex quantity here. So basically, the photon being traveling in the that Van der Waals is traveling has got only a complex velocity of cos theta. Then the magnetic fields are have the same form, so that they are one and the same. Here we can choose e to the I pi over 4, or at 45 degrees. This could also be positive or negative, or I've used it here negative, because that would be the sort of least action if we add as remaining with a real term here. So this would be the least, the most economical way of looking at it. And then these terms, sec theta here, which is basically cos, or sine over cos. The square roots, because I will multiply, because when I look at the energies, multiplying A times R. So I just want a sine over cos term. And then because I've got this term R here with the energy, I introduce a linear R here. So this is reduced to some of value. So as such, so this is a bit of values chosen for the purpose that I want. And so we have the energy of the circular of phi is HR over xt0, and we have the relationship of the energy of the photon in that superposition to the energy of the particle given as sine cos theta. I think you people might know where I'm going to at this point. We've got the velocities as of the photon as c sine theta, and the I must excuse, I left an I out here. So it's basically the velocity of the particle is I c squared minus the velocity of the photon squared. The perceived energy, adding these energies up, because the one is complex, and the other one is real. Comes to this, and now we add an incremental energy to it by increasing the velocity by a d mu y. So the delta energy would be this term minus the term without the delta uy is in here. Performing a series expansion on this term here gives us this term here. I've got two UYs in here which shouldn't be in there. Energy is force times distance, and force is defined by Newton's second law of motion, which is F equals ma. So delta and the distance it traveled is uy dt, where mi is the inertial mass. Equating this term to this term gives us the inertial mass as the E phi times c over c squared minus u squared, all to the power of 3 over 2. But and if mu y is 0, we're left with mc 0, and then it follows very trivially that E equals mc squared over 1 minus v squared over c squared. So here we have another derivation of Einstein's energy equations without using special relativity. Remember, this was all done in a straightforward Cartesian reference system. Anyway, let's get to which is a hot topic in your group. And Joshua showed us this paper last 2 weeks ago, and he highlighted the somewhat surprisingly net phase shift obtained a 90-degree rotation, a quarter wave plate in one of the paths. This is the experimental setup that Kwiat et al. Used. The half wave plate here and a quarter wave plate there. They altered this, measured at stations 1 and stations 2, and maintain that they get all 4 Bell states as shown in these equations. And my question is, where is the magic happening? Is the magic happening here at the observation, or is the magic happening here where I've now got the cursor? In other words, when the photon goes through the half wave plate and the quarter wave plate. From what I believe, from what I have discussed, is if we apply the Occam's razor to Kwiat et al. Instead of the type 2 crystal, instead of taking the 2 photon sources at the intersections of those 2 rings, we say, well, let's take them from these opposite ends of the 2 light cones that the type 2 spontaneous down conversion crystals produce. Therefore, I've only got horizontal polarized photons in Alice's leg and or path, and I only got vertical photons in Bob's path. And we have the quarter wave plate in here. If it's set at 45 degrees, I will now show that the spooky action at a distance happens here, and that we need to have a, if this is right-hand polarized, then this must, circular polarized, then this must be left-hand circular polarized. And although we started with a horizontal and vertical polarized filters, we will measure a 50-50% distribution behind these polarizers here. This is the only way that I can explain that what Kwiat et al. Have measured, so basically I've now just altered the collection points of the spontaneous down conversion crystals here. These are all just fine-tuning the beams, but this is what they changed, and they measured a change here, and I now show you that how to get to this. This was basically, I will use I showed this slide 2 weeks ago. I think Mark said it is not correct, it will not work, but then once I pointed out to him what Kwiat et al. Observed, he sort of went a bit quiet on his objection to it. But basically, my prediction here is that Bob will measure a skewed polarization, and the source, we use a circular polarized source, as was used by Friedman in his experiments. Basically, a circular polarized light source uses calcium. It's a calcium light source. Calcium is heated. Due to the heating, the calcium vapor is formed, and in the calcium vapor, they excite that with an ultraviolet light. So and then the calcium atom down converts either this through the M-1 state or the M+ state, giving either two right-hand orientated photons. If they go in the opposite direction, there is no momentum transferred onto the atom, or two left-hand orientated not atoms, photons. So if we describe a photon, and we basically take all just the direction of we just use the direction of the photon, the P check, and the rotational direction of R check, as from earlier. And I now formulate a nilpotent interaction, that the superposition of the magnetic fluxes of light beam A or photon A plus a photon B must maintain the Maxwellian condition. In other words, I must be able to work out these equations, that equation set we had, in terms of A, in terms of B, and in terms of the superposition of these two. Then it requires energy conservation, requires that the P being the Poynting vector of earlier, that PA plus PB equals 2 times the superposition A plus B times R times B. So, or basically PA being A sub A cross R sub R, and PB being A sub B cross R sub B. Linear conversion requires, linear momentum conversion requires that PA equals to PB, and angular momentum conservation requires a helicities or the spin SA equals S sub B. Sorry about these boxes around there. I don't know what happened there. So clarifying that one point, that or that first point of the nilpotent supervision, we have these, is basically what I explained earlier, that that these equations must also give a solution. Okay, we start with the two photons. So we have, I should have actually put a +1 and a -1 in there, which are basically, it says here PA plus B equals 0, and RA plus RB are 0, then all four conditions of 1 to 5 are fulfilled. Now, if we polarize, or one of the beams, they were circular polarized. If I now let this equation set, instead of rotating on the XY plane, I let it rotate on a complex Y plane. So it can be either completely anything in between. So basically, if Y theta here is 90 degrees, we have a polarization in X. If Y and anything in between will give a sort of elliptical polarization. But if I look at this, I immediately recognize that I cannot solve the A sub A plus B terms because of this asymmetry. You know, okay, for me it was immediate because I've been, I don't know how many cross products I have evaluated in the past. So what is required for spooky action to happen? I polarize the photon A into a minus plus theta or Y theta, and simultaneously for all of this to remain true, the photon B will automatically, or spooky action at the distance, or no, I could even call it Noether's, or not Noether, Noether's theorem, that of opposite sign to what is here and here. Basically, if I now just look at the superposition of A over AX plus BY, which I work out here, I add them together. So these terms add together, and the axes add together. Remember, all these axes are at right angles to each other. Therefore, all these cross products work. I now reduce this to unit vectors, means that these terms I must divide by the norm of 1 plus I theta, you know, the plus basically unit axes, which are right angles to each other, and I have because these I add two signs and the cosines, I must divide by √2. Now I basically, that has become a unit vector, and this provides a solution to this equation set. And this is what I set out to do, to show that AX plus B sub the magnetic part of A and the magnetic part of B polarized is a solution of this. Now you may ask, if the photons are going in opposite directions, how can I make this a solution into a new direction? So let's just go past this one. Let's go past this one. Where is it? Okay, let's get back to it later. Let's just I will come back to that later. Let's just finish this off here. Of what, if I taken what Kwiat has taken, and if I now add my what I've, or with the knowledge that I, or with my theory to it, is that if the the two photons are either vertically or horizontally polarized, as shown here. I will show this as two photon pairs. If the half-wave plate is at 0, these shouldn't have be. Nothing changes with the half-wave plate. If the quarter-wave plate is at 0, this one should have been in black because it is the same one as that one. If it's a quarter wave plate at 45 degrees, we'll have circular polarization in the from the quarter wave plate. Spooky action will circularly polarize in the opposite direction. For pi over 2, we have these values. For 3 pi over 4, we have this value. And the half-wave plate turned by 45 degrees will, this is the action of the quarter wave plate for 45 degrees. This is spooky action at the distance. And then applying all of this to the quarter wave plate, we get these sets of conditions there. Now, what Kwiat said is that he gets a 90-degree shift with a 45 with a 90-degree shift in the quarter wave plate. He gets pi on the other end. Well, it's quite obvious out of this here, so I don't quite understand his what he fully meant by this, but so that was the, this is where I want to get to, this universal state conservation. This is where I was going earlier. We derived this equation, but we had the photon A and photon B are going in opposite directions. And so in what direction do I solve this? And basically it was what's his name, Tim Palmer's talk last week that that I realized what needs to be done. This is basically, this was only, I realized this only after the talk from Tim Palmer 2 weeks ago, that if we have a physical space, we also need a state space. And basically the physical space is in X, Y, Z, and I have a state space in PQR. Now, this is not that unfamiliar, because quantum mechanics is exactly the same. They put the wave function, the Schrödinger wave function, not into physical space. They also state that the second space is required for that. So in the physical space, I have my equations as fluxes, or I have my equations in potentials, and I have my equations in field. And in the state space, where I have this curly T and a new value P and Q, P equals the sum of all the fluxes, the sum of all the potentials times L0, making it a flux, and the sum of all the fields times L0 squared, making it a flux, must be solvable in this equation. Here I have a position equals UDT, and here I have curly E equals the integral curly T dt. Now, curly E I call the epoch of the universe, and curly T I call the state vector, I call is actually the arrow of time. The time in the, as we know, use it, is just a variable of differentiation and integration. And the arrow of time here now steers the epoch in the state space on a three-dimensional path, which would bring it back, the universe, to its original point, but from the opposite end, so giving us a cyclic universe. That is one way of thinking about it. And the other way of thinking about it, which I am developing, is that we know that the physical space is expanding. So if we have the curly P squared plus the curly S squared equals a constant, that means so the physical space is expanding, the state space must be shrinking if it's a constant. And then when this gets too small, we get a big bang in PQR, and the role of the physical space and the state space have reversed. So this is the other way of thinking about it. So guys, I'm sorry I've taken you onto a huge journey from these three equations. I derived the Maxwell equations. I showed that these are fundamental by deriving epsilon 0 mu 0. I have leveraged these equations into photons and particles, derived equals HF equals mc squared. I have explained the phenomenon that leads to the Bell inequality, and I've given support to the philosophical discussion regarding a cyclic universe. And this is where I'm in, and I'm shatteredly have a cup of tea. Thank you. Questions?
So can y'all hear me?
Yes, Luke, I can hear you.
Okay, so yeah, I'm actually Adam. Luke is my son. I'm using his white box as so that I can see your slides. And I just wanted to say, man, I really appreciate you doing this. It's so obvious, you know, you've put years of your life into this work, and I feel really grateful that I was able to attend today. You know, it was just really, really great. I'm looking forward to watching the video of it, and picking up some points. I don't have the background in this that the rest of you guys do. So I'm really much more just as a spectator, just somebody that's interested in these topics. There was something I noticed that I just wanted to ask about it. And it may just not even make any sense. I just noticed it, and I thought I'd throw it out there just in case there's anything interesting. On slide 14.
Which one?
Slide 14. So that one. Yeah, I don't know why, but something about this reminded me of the Cauchy-Riemann equations. And the reason I sort of picked that up again later on in the talk is because you started talking a little bit about complex velocities. And I was just wondering, just because I've been studying this recently in complex analysis, is there any like role of this test for holomorphism, does that have any relationship to anything that you're talking about here? Or is it just sort of a cosmetic appearance that reminded me of this?
Excuse my ignorance. What morphism?
Oh, I'm sorry.
Morphism?
So there's in complex analysis, there's this test for holomorphism. It's the Cauchy-Riemann equations. So basically, if you put a function in the form of a real part and an imaginary part, and it conforms to these equations if it's holomorphic.
Sorry, I'm not qualified to answer that. I've got no. I don't know enough about what you're talking about there. I'm.
Okay,
I've
well,
got a very,
that's fine. I'll just ask at the student
let me-
geometry
but
seminar.
before you go, what I need to show you here is these two terms and so it's p dot grad times u, and the u dot grad the convective operator. And I find these two, there is a lot more. I set them to 0 here, but if the velocity is of light varies with x, then these values are no longer 0. And so somebody who's got more vector algebraic knowledge of this might be very interesting, because this would explain the photons curving around around the gravitational potentials. If on this, because basically I'm working in a linear or in a straight Cartesian coordinate system that doesn't distort, and physics is working in a space-time where the space-time distorts with mass, but I need to distort something, and basically I've got that work on hand. I need to distort the speed of light to get the same results for planetary motions, and I'm sure this will come out of these 4 terms here when they're not 0, but I don't know how to evaluate those.
Okay, and there is one other thing I wanted to ask about, which I think is on slide 30. So yes, so these elementary quantities yet undiscovered. I was curious, this was related to a question I feel like I've asked many times, and I think I just don't quite have the background to understand the answer yet, but I just like to keep asking it. Is this related to this question I've always had, which is time itself quantized? Like, is there a quantum of time?
No, it's I said earlier, it's a variable of integration and differentiation.
Okay, thank you.
Anybody else? Chantal?
I probably have a lot of questions, but I need to think about this first more.
Let me get back to the stop screen share. Where is it?
Can you share the slides so that we can go over this on our own? Or I guess we have the recording, so yeah.
Yeah, no, the slides are all available. They
yeah, okay.
If you look on the Why does it say new share here? How do I get out of share? Here it is. Okay. Now the slides are all available. They on my website. They basically they're all on the announcement that you have. So and basically I've okay. So sorry. If you go to that there on top, that URL neophysics.org/p/1823, you get to the slides as well.
Okay, thanks.
Okay.
Okay, and one more thing I wanted to say, I did record it. I know somebody else was as well, but is there a good place for us to put it so that the recording becomes part of the, when people are coming here to look at the materials?
The material, it's on Jarek's site, and it will also be on my site.
The recording will?
Yeah.
Okay, great.
I'll upload it to YouTube too. Yeah.
Okay.
And Derek, he can link it to YouTube.
In all the excitement of getting this going, Chantal, I didn't record it, so if I could have the recordings, if you can put them onto, if you can somehow get them to me via Dropbox or something, please.
Sure.
Let's see what
Anton, just a comment that is fantastically interesting work, and thanks a lot for putting in all the time and effort to show it to us. And hopefully we can chat about it at some point. I actually come from completely the opposite direction, but I think there's a lot we have in common in the way the stuff that we find. So it's great to hear. Thanks a lot.
Okay, pleasure. Anything further?
Just a quick word from Anton to say how much I enjoyed the presentation, and you really have, as others have said, put an enormous amount of very sort of deep and careful thought into this. As I say, I don't think I have sufficient background to form a complete judgment of the program, but I do think it's very bold, and it obviously connects with ideas which have been out there on the in the background of ever since Poincaré, very overlooked and neglected within the tradition, but still more than worth pursuing in the way that you've been doing. I'm going to write you separately. I got a reaction from Basil to your note, which I'll write to you about separately, but probably not for a day or so, because unfortunately I'm very, very tied up for the next 24 hours. But thanks very much again for the talk today, and I look forward to the next one.
Okay, thanks. Okay, anyway, I'll hear from you later then.
Yeah, I will send you an account of Basil's reaction, and I hope very much we're going to get your experiment done at some point. Your proposed experiment.
Oh, good.
Well, no, I can't.
Yeah, okay, let's not talk about it here. We'll talk about it separately.
Exactly. Let's talk about it on a separate channel. Okay, thanks.
Okay, thank you, Mike. Okay. Anybody else? Chantal, do you want to stop the recording and call it a day?
Yeah, actually, I did.